We have seen in the previous part that missing data, of course, require very special attention when it comes to analyzing longitudinal data. And of course, in most practical situations, missing data will be a problem one is confronted with. What we have seen is summarized in a nutshell two main things already. First, there are a number of simple methods like complete case analysis, last observation carried forward, other simple imputation methods, etc., that we'd better not use. There are always exceptions to everything we say, to everything we do, but as a general feature, these methods really belong, as has been said, in the Museum of Statistical Science. On the other hand, we do have a number of tools available now that are making it or have made it into the toolkit of primary analysis tools. There is, for example, the ignorable likelihood, the ignorable Bayesian methods, where we combine the beneficial dimensions of ignorability on the one hand, which under MAR and using likelihood or Bayesian inferences means that we can analyze the incomplete data as they are without filling in data, without deleting data, and actually usually without much additional programming work, sometimes not even anything. We also have, when it comes to important frequentist methods like generalized estimating equations, we have seen there that even under MAR corrections are needed, and that could take the form, again, for example, of IPW, inverse probability weighting, where we weigh somebody's contribution as a whole, or sometimes individual measurements, by an appropriately constructed weight. And those weights, a way to think about it is, they can be seen as a way to bring the population back in line with the sample, or rather the other way around, bring the sample more in line with the population to compensate for distortions that have taken place precisely because of missingness, dropping out, etc. Inverse probability weighting also generalizes further to a doubly robust method sometimes, but we won't go into those details. What we have seen as another main paradigm for primary analysis is multiple imputation. And in multiple imputation, what you do is you fill in the missing data using a predictive distribution a multiple number of times. And that is way better than single imputation, because not only do we do it several times with different values so that we keep a handle on, or we could also say we keep track of the variability increase, the precision loss that results from missing data. But by doing that from a principled predictive distribution, it's a stochastic method rather than, for example, a haphazard method where we use investigators' ideas or expert opinion or whatever you may want to call it. All of this means that we now have a lot of tools available, and also software packages like SAS, many others also, do have a lot of provisions to analyze data in such a way. Of course, all of that is not precluding what we could say the problem of missing not at random. We have, with what I just said, covered pretty much our tracks for missing at random, but for missing not at random, first, it cannot be ruled out, and second, whatever happens under missing not at random, there is very little, if not no hope for ignorability. We need to make a number of adjustments. And let me say, there is no single way of doing an analysis under missing not at random. Well, arguably, and that's something we will look at in more detail now, chapter 35 will lead us into that. What we will do is we will indicate how, in principle, at first sight, such data could be analyzed, but then we will bring forward a number of pitfalls, and that will point us to sensitivity analysis. So chapter 35 makes us ready for the concept of sensitivity analysis. Good. So, in 35, we're going to consider the so-called Diggle and Kenworth selection model, and you already see that we will continue with some forms of sensitivity analysis. So, again, we start here at the beginning of slide 603 with the concept of a missing node at random, fully specified model, where you have a component describing the outcomes, and that's the variable of primary interest. In the toenail data set, that would be indeed the severity of the effect, the severity of infection, or it could be, for example, the amount of affected nail, etc. It could be any variable that we have studied in this course, frankly. And then the second factor is a factor for missingness, but here, because we are now moving to missing node at random, and not to make it too complicated, we will consider dropout rather than general missingness. Because now we allow for missing node at random, both of these factors may depend on the missing measurements over which I'm going to integrate, which means that this integral, generally speaking, does not simplify. So, what could I do? Well, if my outcome is continuous, I could, for example, and that's just one way of doing it, I could choose a linear mixed model for the outcome, and then maybe, as Kenworth and Diggle, or Diggle and Kenworth have done, consider logistic regression for dropout. Now, I must emphasize that this is an example. It's not the way of doing it. It's a possible way of doing it. There are many others. For example, you could use different models. You could use a different factorization. You could use probits rather than logits, etc. What Diggle and Kenworth have done as an illustration, frankly, not much more than that, is they considered a model where dropout now may depend on the previous measurement as well as on the current measurement. Now, there is already a very important, though somewhat difficult, philosophically, not mathematically, but philosophically difficult issue, and that is, it looks at first sight that this model allows us to test for missing node at random. At first sight only. And why is that? Well, suppose that none of the two terms, the psi1 term and the psi2 term, none of the two is present. Then we have, under this model specification, missing completely at random. Suppose the last one is absent, but the previous one is present. That would be missing at random. And if the last one is present, then it's missing not at random. So here is the idea. We might formulate a null hypothesis. Psi2 is equal to 0. Now, if psi2 is equal to 0, and that's your null hypothesis, you can test for it. And if you test for it and you reject it, you go for missing not at random. You don't reject it, you keep missing at random. The thing is that my reasoning is partly flawed. It's true that you can test for it, and it's true what the interpretation of the model is. However, the model, this would be totally correct if I had available the missing measurements. What I can do now is I can fit this model, and I can fit this model in many cases, so it's not impossible to fit it. We might think, okay, it doesn't have the missing data, so therefore it cannot use the model. No, that's not what it is. We can use the model. That's perfectly fine. But of course, what do we have available? We have the missing measurements available. We have the observed measurements available. We don't have the missing measurements available. So the only thing we can do is say we fit two models to the observed measurements. One with the psi2 term and one without the psi2 term, and we compare them. So if psi2 is significant, it means we improve our fit by including that psi2 measurement, that psi2 term is present. The only thing we can say is, had the missing measurements been observed, and had they been such that they follow the model that we put forward, then the interpretation is right. But of course we don't. And even if the measurements all of a sudden would appear, we may just realize it's perhaps missing not at random, but of a different type. or it's perhaps missing at random, but other model aspects have been misspecified, and psi2 simply tries to compensate for that. So the psi2 term is an extension of your model that may come with an interpretation, just like random effects comes with an interpretation, but they are generally unobservables. It's like saying, okay, I plan two measurements, y1 and y2. They have the same mean, and I only observe y1. So I can estimate the mean of y1. And then I say, and then the mean of y2 is the same. Yeah, because that's my assumption. So y1 identifies the mean of y2 also. But that's only because I made a model assumption that you can immediately disagree with. You can say, no. The mean of y2 is twice the mean of y1. Okay, you have a different model. So then we can say, you have a different model. You use 2 mu2 and I use 1 time mu2. Okay, but we cannot distinguish between our models. The models agree in what they say about y1, and y1 happens to be observed. And they disagree about what they say about y2, but that's completely unobserved. Our two models are identifiable because we make them identifiable, but you will say, yeah, but that's pure belief. And exactly, that's what it is. In my simple case here, it's entirely transparent. There is pure belief about the mean of y2 in relationship to the mean of y1. So extrapolation, I extrapolate. Models like this extrapolate their interpretation, but they don't extrapolate the data. The data are not there, so it only uses the observed data still. Well, that's already very elaborately saying that we have an issue. We have an issue of interpretation. We have an issue of identifiability. Example. And I think already the example will make clear that there may be all sorts of things happening, not just what we put in a model. There should be happening. No. Data do what they want. Observed data are what they are. Missing data are what they are. We only don't have them. So this example now, mastitis in dairy cattle. What we have here is data from the University of Reading in the United Kingdom from quite a while ago. And they're concerned with cows, milk-producing cows. And of course, the more milk, the better, because that means more economic profit. At the same time, unfortunately, highly producing cows are vulnerable, susceptible to a disease called mastitis. And that's a disease, when affecting a cow, that makes the milk unsuitable for consumption. So it needs to be thrown away, unfortunately. That's also the regulation, even though if you would consume that milk, you're not going to get ill over it. But still, it's not something that's used for consumption. So the problem is here that we have high-yielding cows, which is good, but that makes them more prone to the disease, which is bad. That's at least the idea. What we have here is data from year 1. 107 cows are observed with their milk yields in year 1, but 27 get the disease and are no longer there in year 2, do not have a measurement in year 2, so there are only 80 cows left. These dropouts explain why there are these little bullets sitting here in year 1, because these are profiles that do not connect to the second year. A complete case analysis would throw them away. A last observation carried forward would simply take all of those guys and carry them forward, but that's maybe not realistic against the background of most cows actually increasing from year 1 to year 2. Okay, we can analyze the data with a simple bivariate, if you wish, linear mixed model, or with a simple bivariate normal model, whatever, easy to do. And that would be the top of the next slide, 605. That's a bivariate model for the bivariate normal model for the two milk yields. And what's now in the ellipse is the only thing that we need if we are using, or if we are assuming rather, missing at random, because then we can ignore the missing data mechanism. Were it not that, one, we want to deviate from that model also. Second, mastitis in itself, or factors explaining mastitis, are of scientific interest. So this is an example where we can say we have Y and we have R, but it's maybe better to say we have the milk model and we have the mastitis model. And in this case, the mastitis is getting mastitis is equivalent to dropping out and have no milk yield. But still, there is scientific interest in mastitis. And often we say the missing data mechanism is a nuisance. And it is, from the milk perspective, but if we want to study mastitis, it's our primary piece of interest. Okay, fitting the model as a whole we can do, but if we for now focus on the parameters describing the mastitis, what we see is an actually commonly observed phenomenon, namely the coefficient of year 1, 225, and the coefficient of year 2, 254, are the same except for the sign, or almost the same except for the sign. Now, that's weird at first sight, because intuitively we may say, hey, wait, Y1 and Y2 are milk yields. They're highly correlated. Wouldn't you expect their effect to be the same? Well, no. Not necessarily, and that's seen if you recode a model. You can do that in many ways, but it's not uncommon to recode it into, for example, y1 plus y2 divided by 2, y2 minus 1 divided by 2, which is a size effect and an incremental effect. That incremental effect is used, but for the size effect actually only the year 1 measurement is used. What you see, and there are no standard errors given, but they would show that the second guy is significant. We also see that here. The first guy is not. It's not so much the milk yield, it's the evolution in milk yield. So, and the likelihood ratio applied here to the coefficient psi2 is highly significant. So it tells us that there is a highly significant effect of y2 in addition to the effect we already have y1. So we need y2 in this model. Okay, what does it tell us? It tells us that this increment is significant and it has a negative effect. So a high increment reduces the probability of dropping out, of getting mastitis. But that's a little weird, because there is a lot of evidence, and really a lot of evidence, that mastitis is more prevalent in cows with a high milk yield. So what's going on here? It looks opposite. Well, first, remember what I said about y2 being completely missing and mu1 and 2 mu1, etc. All of this is valid provided that the model put forward is right, and that we can never know. Who says that this is the dependence on y2? Why not y2 square? Why not y2 to the third? Why not 1 over y2? Why not also the interaction of y1 and y2? We simply don't know, because y2 is observed but only partially so. And maybe, just maybe, the missing y2 values behave totally differently from the observed ones. Had I observed milk yields on those 27 cows, maybe they were all 0. They didn't produce anything, or they all doubled, or something like that. Well, some scenarios will be pretty weird and implausible, but others may well be plausible. And of course, I can make up many scenarios. I'm not a dairy scientist. If I talk to the dairy scientist, or rather, to a group of dairy scientists, I may get a good range of scenarios that they have in mind, and maybe we can work from there. Scenarios. At one point, we will start working with not a scenario, because that's what we're doing here, and that's a pitfall. The moment you go to missing not at random, don't work with a scenario. Work with scenarios, plural. Okay, so the criticism that I'm bringing forward, or the concern, or the care, or the caution, is summarized in what was actually a piece of the discussion to the paper by Diggle and Kenworth. Nan Laird said, you're estimating the inestimable. You can do that only by modeling assumptions. And the effect of misspecification can be severe. There are many discussion aspects, but what this has produced is a range of ways to go beyond that. Change the distributional assumptions. For example, who says that the missing measurement is normally distributed? Maybe it follows a t-distribution. Influence methods can be used. Change the model framework. Go from selection model to pattern mixture, for example. Go semi-parametrically. Consider ranges, etc. And a few of those will be highlighted here. So, in a way, we can say that what we just said was a criticism to the original work by Diggle and Kenworth. Yes and no, because it's good to have a tool like this available. Otherwise, you cannot build a sensitivity analysis around it. But the warning is, don't take it too seriously, precisely because of that missingness thing. Now, it's already 4 years later that Kenworth himself looked at the data again. And that's important. You don't have to wait 4 years. If you do a missing data analysis, you go further and you start an initial sensitivity analysis, maybe by fitting one or a few missing not at random models. Look at it. Look at the data. Look at the model. Look at it intelligently. And how you have to do that, I don't know in general. It's something you have to do example per example. With a background knowledge from the substantive scientists, look at something like this. You might have noticed it before, but what we see is two cows, they happen to be number 4 and 5, increase very rapidly, very quickly. 4 is special because 4 comes out as the lowest value in year 1 and ends up really high up in the pack in the year 2 measurement. Now that's unusual. So the conjecture is cows number 4 and 5 were ill during the first year. Now this is in principle verifiable if you can have access to the data, and even though the data are still there, they are in an let's say an unkept archive, which is hard to assess in Reading University. It could only be done with significant resources, and nobody is willing to pay that at this time. So practically the information is lost, and we have to leave it at a conjecture. So we already know that there are 2 cows with a high increment, and that's a suspect. Now these 2 cows happen to have a second milk yield. 2 high yields that actually keep being in the study. That's consistent with our original analysis, right? Saying that a high increment is indicative for not dropping out, contrary to fact. And now the suspicion is, aren't these 2 cows responsible for that? Now, it would mean that 2 cows can have an enormous impact already on the analysis. 2 out of 107. Is that possible? Because it's only 2% of the data. Yes, we all know that a few observations can be much more prominent in the analysis than their sheer size, than their sheer fraction indicates. And we call that influence, influenced subjects. So what we do here is we look at something called local influence. And that's something which was developed as an earlier sensitivity analysis tools. So the way it works is you start from the missing at random model. Missing at random first, and then you add a so-called perturbation to it. Now in a course like this, we are trained almost in a Pavlovian way to think, a parameter per subject, that's a random effect. Well, it's not intended to be that way. It's more like calculus-like, other than random effects-like. What do I mean by that? The omegas, for example, are all 0, all of them, except a single one, which is very, very small, tiny, minuscule, infinitesimal, we say mathematically. So a way to think about it is keep them all 0, but for cow 6, let it gently go to 0 so that it almost becomes 0 and see what happens just before it disappears. That's what we call calculus. You do that for 6, 7, 8, 9, and actually you also did it for 1, 2, and 3, and then you do it for 4 and 5. And the question is, does that make a difference? Is there a qualitative or quantitative difference if you look at 4 and 5 relative to the others? likelihood displacement, what is that? Well, it's the likelihood under standard conditions, and where the omegas are all 0, and it's the likelihood where you basically see what happens if you approach 0, but you start from infinitesimal values. Now, of course, I can do that in my initial model, but you may remember that I recoded the model into a main effect and an incremental effect. And maybe the increment, because that's also what we saw graphically, is the more natural quantity to study. So this is already a choice, of course. And if you have a feeling it's ad hoc is maybe not a nice word, it has a negative connotation. What we mean by ad hoc here is actually meant very positively. We make use of what we know about the example. That's entirely different than if we would say ad hoc, indeed. Okay, so what we'd see next is what this likelihood displacement is going to be. So just imagine there are 2 observations only. We have a data set with only 2 cows. I know it's not realistic, of course, because we have 107. But the thing is, with 2 cows and a likelihood, I have 3 dimensions, and that's as much as I can do on a graph. So what is this likelihood displacement? Think of a contact lens lying on the table. Now, that contact lens is basically having at its center, its lowest point, the likelihood at maximum. And then the likelihood displacement is how quickly you move away from that optimal value. And just imagine that the climb in the direction of omega 1 and the climb in the direction of omega 2 is completely different. It tells you they have a different influence on the conclusion. It's a certain curvature we are looking at, and that's what we will do. We will look at the curvature in any direction. I can look at the curvature in one direction, and I can look at the curvature in the other direction. The thing is, curvature is 2-dimensional. It's a curve, and I can look at how curved that surface is in each one of the 107 directions, and that's very important because this allows me to use standard methods even in the face of a surface that is huge dimensional, because as a whole it's too difficult, it's not possible to plot it as such. Okay, now, so that normal curvature can actually be split further in a contribution for the milk parameters and a contribution for the mastitis parameters. And of course, you get the concept that some of the technical details of how you go from one step to the other are actually fairly elaborate. They require quite a bit of numerical analysis, but, not numerical analysis at the end of the day, yes, but actually a certain amount of geometry, and we're not doing that. We're just looking at the major picture. So that curvature can actually be expressed in terms of relatively simple quantities. And what is h? H is the direction in which I look. And to fix ideas, you can look in the direction of cow number 4 and in the direction of cow number 5. How would you define that? Well, cow number 4 is defined as not 1, not 2, not 3, yes 4, not 5, etc. So it's a 107-dimensional vector of zeros with a single 1. What is then delta? Delta is the first derivative, and L double dot is the second derivative of the log likelihood function. So it's fairly simple to derive that. How do you proceed? Well, it's easy to do. You fit a missing at random model, and that's good news because the missing at random model is ignorable. So you can fit the linear mixed model or the bivariate normal model if you wish to the milk model. You can fit to the dropout model or the mastitis model, in this case the logistic regression model, and then you have what you need to have. And then everything else here can be done with simple algebra without having to go through iteration or fitting complicated models again. All right, let's apply this to the mastitis data. And what we do here is we look in every direction of every cow separately. That's what I have circled now. We would expect one graph. No, we expect three graphs. Why? There is the overall influence on the entire vector of parameters, on the entire model. There is a contribution to the milk only, and there is a contribution to mastitis only. First and foremost, overall and mastitis looks very similar. In milk, not so much is happening. There really not so much rises, I should say, above sea level. There are some peaks, etc., but there is no peak that especially stand out. But that's another matter here. 4 and 5, and why are we not surprised? But also 66 comes out. And yes, if we look at the plot, some of you again might have seen that already. I didn't mention it yet. 4 and 5 come out, but so does 66. It's the same and it's different. It's similar and it's different at the same time. It's different because it's high from the start, but it ends up as the highest in year 2. So it starts high with a huge increment. The huge increment is shared with 4 and 5, but the starting point was different there. So 4, 5, and 66 should be examined. Now, if we go back a little bit to the original analysis, that's already a while ago. In the original analysis, we had a likelihood ratio of 5.11. So a test for Psi2, and if we're not careful, we would call that a test for missing node at random, was significant. Kenworth did his informal sensitivity analysis, and he found a likelihood ratio already after removing 4 and 5 of 0.08. So 5.11 comes down to 0.08. Whereas, if we now also remove 66, it's already small and it goes down further. Nothing remains of the likelihood ratio test. Nothing remains of the so-called evidence of missing node at random. So it means, it underscores, one, that we have to be very careful when we call something missing node at random. Second, we also see that maybe there are other features, there are other reasons why the first model at least looks missing node at random. What would that be? Okay, I think we have a good idea now. 4 and 5 are unusual in the sense that likely they were ill in the first year. 66 may just be an unusual outlier, but the three of them together, they go from low to much higher. So they have a positive increment, a huge increment, and they are completers. So almost by contrast, then it's assumed that the ones not completing are different and would have a smaller increment, and it gives the false sense. That mastitis is associated, or protection against mastitis is associated with a steep increment, whereas most cattle farmers would tell you, no, it's the other way around. If there are these huge increases, that's fine, but there is a strong risk of mastitis indeed. I need to explain one more thing, that is H max. Each of those points on the index plot in the first, the second, and the third indicates a direction I look in, a different direction. In 2 dimensions, I look in the latitude and the longitude direction. In 107 dimensions, I look in the direction of each of the cows separately, one by one. But the last graph here looks at a linear combination direction. It's a combination of all of those guys combined. So I don't choose the direction, I define the direction by a criterion, and that is, in which direction do I have to walk, to have the steepest gradient. If you visit a mountain, is the steepest gradient going to be the longitude or the latitude? Well, likely none of the two. Mountains don't know about longitude and latitude, they just position themselves the way they want to, so it may well be that you're having the highest climb under a 45-degree angle or something like that. So here is the highest climb dominated by 4 and 5 and 66 with reasonably similar magnitudes, but with opposing signs. So it it converts, it reflects what we see on the right-hand side. We have steep increases in all three. That's what makes them common. That's what makes them stand out here. But they do so at a different level. The overall magnitude is different. The increment is the same. And that's not making it a surprise why they come out differently indeed. We can go further and decompose the influence. We now know influence is located on the mastitis component. But then the question is, what feature can we interpret that further? Yes, we can. One of the advantages of this local influence method is you can decompose it into meaningful quantities. First, well, dropping out in this case is binary. You drop out or you don't, and that's what it is, because the first time everybody is there, every cow is there, the second time 27 are missing. So there is a single 0, 1 variable that does the trick, and what's the variance of a 0, 1 variable? P times 1 minus P. Now, of course, it's very hard to see something standing out there, because P is a probability. A probability times 1 minus a probability lies between 0 and 0.25. You're not going to see very spectacular things there. The increment or the predicted increment. Why predicted increment? Well, for a missing cow, you don't have the second measurement, so you need to look at the prediction of the second given the first. But brief, for an increment, there you see that 4 and 5 and 66 come out indeed. And then there is what we call the equivalent of the hat matrix diagonal that stands out a little bit, but not really very much. So it really is the increment, and not much of the in the other features in the data contribute to this. Okay. Now, we could also do global influence analysis or case deletion. It's sometimes also called case deletion. What does that mean? One by one, I delete the cases, and then I check how much that changed the likelihood. Isn't that simpler? Yes, methodologically yes, but in terms of actual practical calculations, no, because by removal of every one separately, it means you have to refit your model. You're missing at random and you're missing not at random model separately again. So what does it mean? In the local influence analysis, I fit one MAR model and that's it. And everything else are deterministic calculations based on the output from that model. I don't need to fit any other model. Here, yes. I have to fit initially the missing at random and the missing not at random model. And then I have to do those two models for one by one, removing every one at a time. So you remove one and you fit number one. You remove cow number one and you refit the model to the remaining 106 cows. And if that's done, you put one back and you remove number two, etc. So you have the original model, and then you can remove one by one 107 cows. That brings it to 108 times 2. It's 216 models. So local influence may take a minute. Global influence may take 3 hours or 4 hours. That's without kidding, really what happens. So it's interesting for us to actually look at a variety of subsets. We're not going to do the one by one now. We're going to look at all data to begin with as a benchmark, then removal of 53, 54, 66, 69. And where do they come from? Well, they're the ones that come out of a local influence when psi2 is associated with y2. In the original formulation, we can look at 4 and 5 based on Kenworth's views indeed. 66 is the one that came out of the previous analysis and was not with 4 and 5, and then we can look at those three together. One remark, if you look at y2, which may make sense at first sight, y1 and y2 are highly collinear, so it's very hard to get something meaningful out. If you recode in the increment, that's a different story, and there we do get meaningful interpretation. So we have to think carefully about the parameterization that we use. And what parameterization is the best? How should I do that? that's something you need to be aware of. You need to be aware of the fact that it needs to be done, but how it's done in practice, that will depend on the practical example that you're actually using. Okay, here is the result, and you see, of course, that the likelihood changes from all to one of the removals, but that's, of course, evident. If you have different numbers of subjects in your data set, that has an implication. It's more meaningful to look at what's happening to the psi2 parameters. You know, initially, the psi2 parameter was significant. If you remove all of the guys from the original local influence analysis, you still have significance. If you remove 4 and 5, that significance has gone. If you remove, interestingly, 66 on its own, not really. If you remove 4, 5, and 66, nothing is left of the effect whatsoever. Is there an effect on the parameter delta, for example? Well, under MAR, removal doesn't have a lot of impact. There is a bit of impact indeed. In the case, look at it carefully. In the case of missing not at random, if you take the original data, you have a significant delta at the end still, but the magnitude has changed. So a removal of 4, 5, and 66 under missing not at random does have an impact on quite a few parameters. Even the correlation is medium, versus the correlation is much higher after removal. So you do get a different picture. And interestingly here, with the removal 4, 5, and 66, parameters before and after fitting the MNAR model versus the MAR model are fairly similar, which was not the case here. So that tells us, looking at the likelihood ratio and the similarity of the parameters, that really those observations that were responsible for giving the impression of a missing not at random mechanism, those observations have gone and nothing is left of missing not at random. Are we now sure that the mechanism is missing not at random? No. And it could still be playing in another way. It only explains now that within our model concept, what seemingly looked like missing not at random is actually completely gone. Okay, good. So that brings me to the end of the first analysis, chapter 35, where we have on the one hand indicated that a missing not at random model can be fitted, but immediately we started looking at the need for sensitivity analysis. Kenworth did informally by just graphing the data and giving thick lines to cow 4 and 5. Then we, in a principled fashion, looked at sensitivity analysis, and that was using local influence, and we contrasted that with a more straightforward, but much more computationally intensive global influence. Okay.